talk a little bit about building a little CPU that I've been building for myself. So the background is I got a TinyFPGA BX board for myself, and I'll explain what that is in the next slides. And I got it for myself for Christmas a couple of years ago. I did a little bit of messing around with it. I did a talk about it 2 years ago, maybe at the last in-person Raspberry Pi. And then I got completely distracted and moved to Germany. And I've only in the last few months got back to doing anything with it. And so in this talk, I'm going to talk about what I've done with it recently. So briefly, what's an FPGA? It's a field programmable gate array. So it's a little chip. It's a chip that's full of logic gates, which most chips usually are. So when it says array, that means lots of them. And the interesting thing is that they're field programmable, which means instead of being connected in ways that are wired in at the factory, you can download the connections essentially in the field, which in my case means sitting on my workbench. So the use of these would be if you wanted to you wanted to build a custom chip, but you're not really building you're not going to make enough to build a custom chip because it's quite expensive to get started. Or maybe you want the ability to upgrade that chip in the field. Say if you live in that Apple Google mindset where there's always software updates, this allows you to kind of install a chip in your phone, for example, when you manufacture a phone, and keep fiddling with the hardware over time. So logic gates are things like an AND gate, an OR gate, a NOT gate, XOR gate, things like that. I'm not going to go into really any depth there. If you put them together in the right way, you get useful digital circuits. So if you, for example, you can combine two XORs, two ANDs and an OR, and you can make a little circuit that can add two binary digits. So for example, it can add 1 + 1, or 1 + 0, or 0 + 1, or 0 + 0. And if you have a lot of these together, you end up with a computer. So going back to that FPGA definition, we've got many gates like this. The field programmable bit means we can choose how they're connected to each other, but it also means we can choose what each gate does. So instead of being given a certain number of XOR gates and a certain number of AND gates, we're given this more general thing called a LUT, which is called a lookup table, which is this sort of programmable gate. And I can say, I want you to behave like an AND gate, or I want you to behave like an XOR gate today. And every time I download a new image or program into the FPGA, I can make that gate be a different kind of gate. So it's this sort of weird half universe that lives half in software and half in hardware. Okay, so what's TinyFPGA BX? Here's their picture. It's here's their production picture. Can you see my mouse cursor moving around?
Yes.
Yes. Okay. So here's the actual FPGA chip. It's very small. So a little bit like if you look on a Raspberry Pi, the actual guts of the device are this tiny little thing. And most of this board is just getting all of these pins wired into the FPGA. There's also a USB connector, which just wires straight into the FPGA. There's a power LED and there's a controllable LED, which wires in. And there's this, which is a 1 MB flash ROM, which is wired into the FPGA. So you get this nice breakout board. All of these pins are just sort of general purpose IO. They're not fixed to any function. They just go into the FPGA and connect to however you program them. So they might be if you implement an I2C bus, then pin 6 is I2C, or it could be a serial port if you implement that serial port hardware in here. So there are no fixed functions at all. They're just wires into this fabric of programmable gates. So costs about $38, but it is on back order, like everything seems to be these days. So when I checked earlier today, they said they would be able to deliver by September this year. So I think that's just a global problem with chips at the moment. So this kind of looks quite like an Arduino or a Pi Pico or something like that, that it's the chip with lots of pins that you can stick it in a breadboard and attach whatever you're going to attach. And by default, when you power it up, the FPGA loads a default configuration that turns it into a USB bootloader that lets you program your own user configuration. So it works quite like Arduino does. You basically stick your computer attached onto this USB port, and you can download a new image of how the connections will be made. So my current FPGA project, the previous projects I've done were just simple things like flashing LEDs and working with rotary encoders. My current project is building my own CPU called Shitty CPU 40. It's shitty CPU because it's quite shitty, and it's 40 because the FPGA chip here is called an ICE 40. That's the manufacturer's name for the actual chip that's used. So what's a CPU? I'm a computer programmer by heart, so I think about things in terms of computer programs. So a computer program says what your computer should do, and a CPU is the piece of your computer that follows that program. Okay, and CPU stands for Central Processing Unit. People also call it a microprocessor, and that's things when people talk about ARM or Intel Core i9. That's the CPU that they're talking about. So to get a real computer, you would get a CPU and you'd add on stuff like memory, some graphics stuff. If it's a phone, you put on a touch screen, some network stuff, disk drives, things like that. And you add all of those onto the CPU to give you a full computer. So the TinyFPGA board came with a couple of demo images, and one was actually a demonstration CPU. So that for me was a nice proof of concept that it is possible to build a CPU on a small FPGA like this. So it was a CPU that implements the RISC-V instruction set. And so one of the reasons that you would use something like this is, say you built some specialized hardware on your FPGA and it needed a little bit of control. Well, rather than building a complex control system, you could say, I'm just going to download a CPU off the internet and put it on my FPGA, which is kind of a strange concept to be downloading hardware. And then when you've done that, you now have access to a standard RISC-V C compiler. There's a Linux distribution if you made something big enough. And if you're doing stuff on FPGAs, not because you care about CPUs, maybe you're building a network router and your FPGA work is on building fast network routing hardware. You don't really care about the CPU. You just want to get one and be done with it. But all of those reasons are reasons for me to not run Pico RV, that RISC-V CPU on my FPGA. I want to play with this for a hobby. I want it to be complicated. I want to have to learn how to design good instruction sets. I want to spend the whole evening trying to understand why my add instruction isn't working. Okay, so I don't want to use Pico RV32, the RISC-V CPU. I want to make my own thing. So it's not an enemy, it's more like an inspiration of what proof that stuff can be done. And now I want to start kind of from scratch and build it all myself. So the architecture of this thing, what the inside looks like, what the different sort of blocks of gates that I've put on the FPGA. There's a program counter, which is where's my next computer program instruction coming from. There's an instruction register, which is a 32-bit register. There's a little control unit, which says I'm going to load an instruction and then go through a sequence of states to try and understand, to do what that instruction does. So there's lots of different instructions. I'll show you later. There's also a RAM block that's 8 kilobytes. There's 2 stacks, which are kind of like RAM, but you can only access the top. And then there's also some peripherals that I've implemented. There's a UART, which I just copied from that Pico RV design. So that gives me a serial interface, which I've then got connected to a PyPico into my laptop. So that gives me a little screen keyboard console to talk to my CPU. There's a speaker driver that can make beeps, and there's an LED that you can have either on or off, LED style. So everything in this CPU is 32 bits. It's not byte based, so every instruction is 32 bits long, and they look like these big long hex strings, which are not very human friendly. Every memory location is also 32 bits, not bytes like on a conventional computer. And part of the reason for that is it's just easier for me to just have one size of thing, one size of object, or one size of number, and 32 bits is the number that I chose. So I've had to choose which instructions my CPU will have. And I started off by just saying, well, let's build a very simple program that flashes an LED. What instructions do I need to do that? And added just the bare minimum instructions to do that. And then as I've tried to make more advanced programs, I've discovered that I need more instructions, and I've implemented more instructions to let me write the more complicated programs I wanted. So that's not a very principled architecture at all. Things like ARM or RISC-V or whatever, people sit and try and design instruction sets and make them coherent. Well, mine is just organically grown. But I am pushing towards a bit of a principled architecture, that it's a stack-based architecture, which is, if you've ever used the programming language Forth, then you'll understand what that is. If not, it doesn't matter too much. But I'm having fun with this. I'm a programming languages person, so designing my own programming language that runs on hardware is a big part of the fun for me. And then to go with this, I have an assembler, which is just a program that takes, it's going to take human readable text that I've made that looks more like a normal programming language and turn it into a sequence of these hex strings, which are the actual instructions for the CPU. So this is the instruction set that I've ended up with as of today. So they're sort of divided into sections. If I just want to stick a value on the stack, there's a load instruction. I've got a go sub and return for making function calls. I've got this complicated jump back non-zero instruction, which lets you do if statements. There's a few instructions here for rearranging the stack. So these are three fundamental ones that you need for doing stack kind of computing. A little bit of maths. I've just got add and decrease by a certain amount. Turns out I haven't needed any other maths so far, so I haven't implemented them, but I'm sure they will come. And then I also have some instructions for interacting with the peripherals. So there's an LED command, which will turn the LED on or off. There's the console UART, which is the serial port. There's an instruction to initialize it, and an instruction to write a character and to read a character. So this is how I can get a character to appear on my laptop screen, or how I can read a character off my laptop keyboard. Tone gen is the speaker tone generator, and sleep is, if you call the sleep instruction, it will just delay for a little while. Okay, so I'll show you some code snippets at the end of this talk. I'm just going to scroll through them. So there's a really nice open source toolchain stack to go from writing the human readable code to go to the FBI, go to the FPGA. There's a tool called Yosis. There's another tool called NextP and R. And what they do is they take a kind of abstract description that I'll show you in my windows at the end, and they turn it into an exact description for the FPGA that says this block, this gate must be an XOR gate, and it must be wired to this block, this gate over here, which is going to be an AND gate, for example. Okay, and then when you've generated that configuration, there's another tool called TinyFPGA, which actually downloads that onto the chip. So the CPU design so far, how much of that FPGA have I used? So the big thing is the number of LUTs, which is this top line. And so far I've used 23% of them. There's also some RAM on that FPGA, and I've used just over half of it. So I'm not too concerned about that because I know how much I've decided to allocate. This number is a little bit not random, but it's a little bit unintuitive. Sometimes I make a very small change and it really changes how many gates need to be used for the design in ways that I don't have a good intuition for. And then this is IO ports, 7, probably because I'm using seven IO pins, and then the rest are a few internal bits. So I've used 23%. So I've got plenty of space left for adding in more instructions and more complexity. So the future, this is an ongoing project of just me doing stupid stuff that I feel like without any particular end goal. I kind of feel like I'm going to end up with a little computer that's about the same capacity as probably a mid-late 1980s home computer, based in terms of the clock speed and the amount of memory available and things like that. So here's a random grab bag of things that if I feel like doing, I will do them. So the first one is that the program code instructions are all loaded out of RAM in the FPGA at the moment, but there is this flash chip attached to it. There's a megabyte of flash chip. So I could make it talk SPI to the flash chip and load programs out of there. That would give me a huge amount of extra program space. It would be almost a megabyte compared to 8 kilobytes of RAM. So I'd be able to fit a lot more in there. I love my NeoPixels, so implement some NeoPixel driver perhaps. I've got a micro SD adapter board that's been looking for a use case, and this might be the use case, so I could give it a little micro SD drive. There's some more LED stuff called Charlie plexing that originally I started off, I think, just trying to write a Charlie plex driver, which is a way of controlling LEDs, and got completely carried away building this CPU and never got around to building the Charlie plex driver. If I wanted to build a multi-core version of this, well, to start with, I can just tell the software, lay this same circuit out twice on the same FPGA. And that would just be a one-line addition to say, do this twice. And then I would need to put some kind of communication between those two separate circuits. And then I would have a dual core CPU on my FPGA. There's all of these extra pins, and I haven't got a use for them. I think there's 24 logic pins and I'm using about 4 at the moment. So I was thinking maybe I could implement some pieces using discrete logic chips maybe and stick them on. That might be a fun adventure. There's also the USB port. There's no USB driver hardware at all. That USB port just connects to the FPGA, and whatever you want to drive that port, you have to implement in FPGA logic. And I'm kind of scared to try doing that because USB seems very weirdly documented and complicated, but it might be a fun thing to do. And the last thing is I expect I'm going to come up with a need for a lot more instructions as I build more software for this. Okay, so I'm going to show you, that's the end of the slides. I'm going to show you here. So you should be able to see a text console at the moment. And
Yes.
Yeah, this is what the language called Verilog looks like. So it looks kind of like a programming language, but you can see I said here, I want you to implement a UART and use the UART library. And then this says how wires, conceptual wires inside the device are connected. And then down here, I've said, I want to use my speaker library and connect these wires together. Down here, I said, all right, I want you to load it, fill the instruction register with the value of the RAM at the position of the program counter. So it kind of looks like a programming language. but it doesn't behave quite like that because it's controlling hardware, not software. And I'm not going to go into any more depth than this. It's a bit complicated, but it's interesting. And then I've also implemented an assembler. So you can see here, this is the machine code of the CPU that I have implemented. So you can see here, I've got some test code that says output this string over the serial port, over test should see ABA, then do some stuff, which does some stuff with the stack and writes 3 characters to the console. So when this line runs next to the should see ABA, I'm hoping if it works, it's also then going to say ABA if my CPU is implemented correctly. So I have a few tests like that. I'm going to run this program in a couple of seconds, but it's basically extremely very simple machine code. It's nothing like Python where you can define objects and talk about floating point or tuples of red, green, and blue. You're just doing these very simple instructions that are store this number on the stack, send it to the serial port, compare if it's equal to 0, things like that. So you have to build everything out of these incredibly rough units. If I run that, so what you're seeing now, hopefully, is Minicom, which is a serial program, and it is attached to a Pi Pico, which is just forwarding its serial port to 2 of the I/O pins on FPGA. And if I push reset, which I'm going to push reset now, there we go. So this is the CPU running that program. So the CPU has been downloaded onto the FPGA, and the CPU is now the CPU that I've put on the FPGA is now running that program that I just showed you. And up here you can see over test. That's the thing I showed you before. We should see ABA, and we do indeed see ABA. So that little bit of the code is working correctly. That wasn't working last night. It was causing me a lot of trouble at midnight. So now all the rest of the program does is just when I push a letter, it comes down over the wire and sends it back. Okay, oops. So when I say hello world like this, it's not that these characters are doing a round trip into my FPGA, into the CPU, into a program, and the program just sends them straight back over the serial wire. Okay, and the last thing I'll do is turn off my screen share. And if you look at my screen, I will try and show you what a tangled wiry mess this looks like. There's the speaker, which I'll put down, and then I have this long breadboard. At one end there's the FPGA, at the other end is my Pi Pico, and I just got an LED for a controllable LED, and then 2 LEDs for the receive and transmit serial wire. And here's the receive and transmit serial wire. Okay, that's my talk. Let's have a look at the questions. Okay, HB calculators. Yeah, definitely HB. Definitely HB calculator like. Some stuff about FPGAs. Yeah. So Bruce says, yeah, 30 years ago, this needed a lot of very advanced tooling. There's actually one of the things that was nice about the TinyFPGA was it was the first FPGA board I saw that really was set up for essentially my place in the market, which is just some guy sitting at home that doesn't want to buy $1,000 development license and doesn't have access to a lab, is just basically doing kitchen table style development. That space seems to have really got better in the last few years, which is pretty exciting. Is there a place where you can download parts of code that you can pull together? I haven't seen any one place. So the UART, the UART on this I did pull out. I downloaded it off the website, off the GitHub for Pico RV32, that CPU that I talked about at the start. And their UART was just nicely packaged up in a module. And I just copied that file completely and didn't edit it. So I'm not sure. The tradition there, I think, is still a little bit commercial. So, for example, people will talk about using an ARM soft core where they buy a license to use a design for an ARM chip, but that's all much more commercial. It's not like a free repository, because that's how they make their money, is by selling a license to use those soft cores. Ruben asks, how did you create an assembler for your CPU? It's got a little bit tangled, but in the essence, it's just a little program that you could write in Python or whatever that reads in a file and says, oh, you said console write. Well, I know I need to output the number 5,000. Now you've said push. Well, now I know I need to output the number 6,000. So the beginnings of that is a very simple translator. There's really not a lot of complicated stuff happening there in an assembler. That's sort of what makes it an assembler more than a full programming language. Is it really, to an extent, it's just turning words into predefined numbers for you. All right, any more questions? No? All right, cool, then I am done.
Wonderful. Thank you very much.